So in my final lecture, before Tibor takes over, I just want to give a brief introduction to what goes on beyond leading order and perturbation theory. We spent the last 6 lectures setting up the structure of perturbation theory. And along the way, we had to make some assumptions. And those assumptions didn't introduce anything new at leading order, but beyond leading order, that meant that if we wrote down a naive Lagrangian, for instance, suppose we were interested in phi cube theory, which has this Lagrangian. Then we saw that to compute a scattering amplitude or scattering cross-section, one of the main tools we used was the LSE reduction formula. And for the LSE reduction formula, we assumed that omega phi omega was 0. And we also assumed that k phi omega was e to the I kx. So these two assumptions meant that we had to change the form of our naive Lagrangian by shifting and rescaling, and also renaming the fields. So these assumptions that our Lagrangian had this form, and that these two statements about the expectation value of phi and the form factor were inconsistent. So we had to shift and rescale in order to impose these conditions. And what we would get after we shifted and rescaled is a new Lagrangian that has some additional factors and one new term in it. So we get a Lagrangian where the kinetic term had an extra factor of z phi. The mass term has an extra factor of zm. The interaction term has an extra factor of zg. And we get a new term, y phi. Okay, so we saw this back in the lecture about the LSE reduction formula. And so today we're going to try to learn how to do perturbation theory with this Lagrangian and see how what these conditions tell us about the various coefficients here. So to do perturbation theory with this Lagrangian, we should break it up into a free part and an interaction part. So we can write L as free part plus an interaction part. And as always, the free part is just the Klein-Gordon Lagrangian. And that means that the interaction part is everything else. And so I'm going to divide the interaction part into two terms. One is just the rescaled interaction term we wanted to add. And then the other terms are the ones we were forced to add due to the assumptions we made in the LSE reduction formula. And so this is what's known as the counterterm Lagrangian. So CT here stands for counterterm. And this is just everything else. So we've got a half z phi minus 1 d phi squared. Similarly for zm. And then we also have our new term, y phi. Okay. So if we want to do perturbation theory beyond leading order with this Lagrangian, we can't because we made these assumptions. So we have to change our Lagrangian to this form. And so that's means we have new terms, and we're going to see what those new terms do in a minute. This is an equal sign here. And okay, so first of all, we know that if we set the interaction term to 0 in our naive Lagrangian, then we don't need to do any shifting or rescaling. These two conditions are automatically satisfied. You computed both these conditions in the Frequenc-Gordon theory. So in the limit that g goes to 0, we should have that y is 0. So y is 0 plus some order g term. And the zi's, similarly, should be 1. We set g to 0. And so they'll have some corrections that potentially could be order g, but we'll see, or at least I'll motivate why later in the lecture, why there are no order g corrections to the zi's. There's only order g squared corrections. So we'll see that later. Okay. So in our new theory, the Feynman rule for the vertex changes. So we still have a phi cubed term in our interaction Lagrangian. So that gives us a vertex with three legs coming out. And in position space, the Feynman rule for its vertex changes just gets, we've changed the coefficient, so the coefficient in our Feynman rule changes. So instead of just Ig integral over x, we get Izg integral over x. So that's one of our Feynman rules, but we also have a bunch of new terms. And these new terms are going to give us new vertices. We'll discuss the z phi and zm later, but first new term we see is that I want to talk about is the y phi term. So this is a strange term. It only has one field. So that should give rise to a vertex where only one line comes out of the vertex. So we can draw the vertex for Iy like this. So here I'm drawing an x on the end of the line to indicate that this is a vertex where one line ends. So we only have one field coming in to this point, and no fields leaving. So this is where a single line ends. And this is slightly strange, but that's what we get if we've got a linear term in our Lagrangian. And the Feynman rule for this is just I, y, that's the integral d4x in position space. Okay. So with these two rules, we are equipped to see what our first assumption in the LSE reduction formula tells us about these new coefficients, y and z. So let's examine this first condition, that omega phi omega is 0. In terms of diagrams, this is just saying that the 1 point function vanishes. So the sum of all diagrams with one external point should vanish. So at leading order in G, we've got a diagram like this. If we have one external point, x, and we use this vertex, we also have this diagram too. So we're assuming that y, so we know y is 0 at order g to the 0. So we expect that y will be order g. So we also get a diagram like this from our new vertex. And if we go to higher order, we can draw a bunch more terms. So we could draw something like this, or a diagram like this. This is all x. Or and so on. So these are the first order G diagrams, and these ones are all order G cubed. And so we need the sum of these diagrams to vanish. So it should vanish at each order in G. This should be hold. This equality should hold for any value of G. So it should hold separately at each order in G. So in particular, at order G, the sum of these two diagrams should vanish. So that was one of the assumptions we made when we derived the LSE reduction formula. So in deriving the LSE reduction formula, we wanted to assume that the phi omega was a one-particle state. And so in particular, phi omega is a one-particle state. It should be orthogonal to the vacuum. We also, the second one basically came from demanding that it was normalized correctly so that the relationship between the field operator and the creation operators is the same as in the free theory for the normalization. And then we got for free that the one-particle states were orthogonal to the multi-particle states. So that's what we did. But, we had to impose this one, that the one particle, that if this is a one-particle state, it's orthogonal to the zero-particle state. Okay. So we want this to vanish. So let's compute these two diagrams and see what that tells us about y. So this first diagram is equal to, so it has one vertex. So we get one factor of I ZG, G. But ZG is 1 plus corrections that are order G or higher. So we can just set this to 1 if we're only working to order G. Then we also, if this is the point y, we also get an integral d4y from the vertex. Then we have two propagators here. So a propagator from x to x and y to y. So I can write down the Feynman propagator from x to y and y to y. Then this diagram also has a symmetry factor of 2 from exchanging the two ends of the propagator from y to y. So that is the expression for this diagram. And then we have the other diagram, which, using our new Feynman rule, we can just write down, so all we have here is a vertex and one propagator. So this is just I, y, integral d4y, this is x, and this is y. Then the Feynman propagator from x to y. And so we can pull out delta f of y minus y. That just factors out of the integral. It's independent of y. And what we get is that omega phi omega is iy plus 1/2 g delta f of 0 times the integral d4y delta f minus y plus higher order terms. And so if this is going to vanish, this doesn't vanish. We need, we can't do anything about this even if it does. So we need to set y, there's an I here, y to be equal to minus 1/2 g delta f of 0. Order g cubed. There's no g squared corrections, as we can see, because the next order diagrams we can draw are order g cubed. So this is our result. So we have to impose this in order to do perturbation theory beyond leading order, this phi cube theory, and impose the conditions we needed for the LSE formula to work. But you may be somewhat concerned here. We've got a delta f of 0, which, just using our definition, right, is the integral of I over p squared minus m squared e to the minus I times p times 0, which diverges. Okay, so we had to do this in order to use LSE reduction formula, the way we've derived it. And we see that y here is infinite. So we can get around this. And the way we can do that is we can regularize our theory. So this integral diverges, but we could modify it in many different ways to make it finite. For instance, we could just impose a high energy cutoff. So we could regularize this result by imposing a cutoff. Lambda. Alternatively, if we wanted to maintain Lorentz invariance, we could also modify delta of f in a Lorentz invariant way, so that we just multiply the expression for the Feynman propagator by some factor that will make the integral converge. There's many other choices. If we do it this way, we would get, using techniques we'll learn about in tutorial this afternoon, this result, which diverges in the limit lambda goes to infinity. But in whatever way we decide to deal with this infinity, what we can do is first regularize our theory by imposing a cutoff, modifying our Feynman propagator or other ways we'll learn about later. And then compute whatever quantity we're interested in. Say a scattering cross-section, a decay rate. And these divergences will cancel out in any physical quantity that we're interested in. So what we do is we regularize our theory, compute what we're interested in, and then we can send our regulator to infinity. Because the physical quantity will not depend on the regulator. So if it does, you know you've made a mistake. And we'll see some examples of how this works. That's the basic procedure. Okay, and for this y, we can, in fact, without really doing any computations, worrying about how we're going to regulate this, just if we assume that it's regulated in some way, we can see that the effect of y is going to basically cancel out it'll just have an effect on which Feynman diagrams we consider. So it's y is one of the easier quantities we can deal with without even worrying about how we regularize the theory. So let's think about what our result means. So basically, we're demanding the one-point function is 0. And so this, diagrammatically, we can represent it by the following equation. So we want this to be 0. And what I mean here is this is just any subdiagram with no external points. And so all of the diagrams we've drawn over here are in this form, and this equation is just a shorthand for writing out this expansion. We wrote the first few terms out. And so this is the equation we need to impose to determine y, order and order by g. So this fixes y. But let's suppose that we've imposed this. So at each, we've calculated what y should be. Should be that expression, delta f of 0. That's some factor minus a half g. But let's suppose we've done that and we've regulated our theory in some way. So then what does this tell us about other correlation functions that we might be interested in? So first of all, let's look at a simple example. So let's suppose we want to calculate the sum of this diagram and this diagram. So where these are external points here, x and y, x and y. So these two diagrams contain these two diagrams as subdiagrams. And this was the point y. Everything that involved y except for this integral d4 y of delta f of y factored out. So in other words, we could pull out this delta f of y, and the same thing will happen over here. So if we have, write down the expressions for these two diagrams, we'll have new propagators corresponding to these lines, but that won't affect the cancellation at all. So the sum of these two diagrams should be 0 at order g as well. Basically, the part of the diagram at z doesn't really care about what's going on down here.
So could you explain how we consider these diagrams?
These diagrams, so these diagrams, it's just one example of a class of diagrams we can consider that has these two diagrams as a subdiagram. And this vanishes basically because we impose this condition at order g. But it's much more general than that. At any order, if we impose this condition, then we have that the sum of all diagrams like this will vanish. So this is guaranteed if we impose this. So diagrams of this form are known as tadpole diagrams. They sort of look like tadpole. And what we see is that if we demand that the sum of all the tadpole diagrams vanish, that tells us that the sum of all diagrams with tadpole subdiagrams vanish.
When you say no external points, how does that external points then fit into that?
So this one here?
Yeah.
This is not, despite the fact that it looks like an external point, the fact that I've drawn an x here means that we're using our one-point vertex. So here, this is an internal point.
Oh, so it's not a line
It's, you can think of it as a vertex where only one line comes out of it. So I've drawn the so here, x is an, so for instance, in this diagram, x is an external point. What we're computing is omega 5x. And so we expect our answer should depend on x. We have this other point over here, y. Our answer can't depend on y. It's, we should think of this as a vertex, and we integrate over it, its position. So this tells us that any diagram with a tadpole subdiagram, the sum of all diagrams with tadpole subdiagrams vanish after we impose this condition. So there's no need to compute any diagram that looks like this, or, for instance, we have more points. We see a diagram like this, or this. There is no need to compute them. Otherwise, based on what we've learned previous to now, there would be no reason, if, say, we're interested in 2-to-2 scattering, that we wouldn't compute this diagram. This is amputated. It's fully connected. But this condition tells us that we don't have to compute any diagram of this form if we're interested in 2-to-2 scattering. So this condition saves us a lot of work. And it's independent of the way in which we regulate our theory. Okay, so that's what our first condition. Our first assumption for the LSE reduction formula tells us. It tells us there's a huge class of diagrams that we don't need to compute ever if we're interested in Green's functions or scattering amplitudes, as long as we impose the LSE assumptions of the LSE reduction formula. We don't need to compute diagrams with tadpole subdiagrams. Let's turn to this next condition. So this next condition is, so we've got, here we're computing k phi of x omega. So this is the overlap of two one-particle states. It's partly in momentum space, partly in position space. So it's related to the two-point function in position space or momentum space. It's sort of halfway Fourier transformed. So instead of considering this condition directly, it's easier to work either in position space or momentum space, where we know the Feynman rules. So let's consider the momentum space two-point function, momentum space propagator. It will be related to our second condition, and see what that tells us. So consider G of P and P prime. And so this will always be proportional to a momentum-conserving delta function. So we'll just write down an expression for G where we've already imposed that P and P prime are equal and opposite. So we can draw the diagrams for G2 of P. And at leading order, we just have the Feynman propagator. Draw more diagrams at next to leading order. And one of the simplest ones we can draw involves our three-point vertex. So this would be there even if we used our naive theory. But we're forced to add new terms. So we were forced to add the y-phi term. That gave us the one-point vertex. We also had to add a new two-point vertex. So we had a new vertex that comes from the z-phi minus 1 and Zm minus 1 phi squared terms. And the precise Feynman rule won't be important for what I'm about to say. But the next calculation will be done entirely in terms of diagrams. So, but we do get a new two-point vertex that contains, that depends both on z-phi and zm. So both of these terms contain two fields. So it should be a new vertex where two lines enter the vertex. So this is a new vertex. This is different from the other vertex. It's different from this and the free propagator. So we're treating this as an interaction vertex. So we also get a term that involves this new vertex. We've got momentum p flowing into and out of the vertex. Could also draw diagrams like this, or like this, but as we've just seen, these cancel. Okay, so next to leading order, these are the only diagrams. So these are the order G squared diagrams. Beyond this, we get a bunch more diagrams. Let me just draw a few of them. So we'll have diagrams like this. A diagram like this. Diagram like this. Also diagrams like this. And others at order g to the fourth. I didn't draw them all, but these are several of the diagrams we could draw at the next order. And so we immediately notice one thing, is that at least the first three of these diagrams I drew at order g to the fourth just look like we've strung together several copies of these order g squared diagrams. And so these ones that are strung together from several copies of the lower order diagrams also have the property that the diagrams fall into two pieces if we remove the middle line. So remove the middle line, these diagrams fall into pieces. This diagram that's not constructed from multiple copies of the lower order diagram does not have that property. If I remove any of these internal lines, the diagram is still connected. So in fact, we can classify or group together all of the contributions to the momentum space propagator. So we can determine them all just by, or we can group them together into classes depending on how many times, how many lines can be removed that divide the diagram into multiple pieces. So in other words, write G2P as, so we have just the free Feynman propagator. We also have diagrams of this type, which I'll call 1pi diagrams, where there is no line, no internal line that can be removed that divides the diagram into two. Also diagrams of this type, where we have two one-particle irreducible diagrams that are connected together, and so on. So here, this one-particle irreducible. So 1pi means one particle irreducible, which means that there's no line that can be removed to separate the diagram into two disconnected pieces. So this is just saying that we can classify the contribution to the propagator by how many different lines there are that we can remove to divide the propagator into two pieces. So computing the sum of all of the one particle irreducible diagrams is something we can do order by order. We can't in general, it's a difficult or impossible problem to compute it at all orders. But let's just imagine that there is some expression that we could associate with the sum of all particle irreducible diagrams, and we can compute that perturbatively. And if there is such an expression, we can write the momentum space propagator as follows. So if the leading order term is just I over p squared minus m squared. That's I epsilon. And the next term has two propagators. So both have momentum p. And then it has one factor of we'll call I sigma of p squared. So this is the contribution from all 1pi diagrams. And the next order term will look very similar, except we'll have the Feynman propagator cubed and two contributions from the 1pi diagrams. So three propagators to 1pi, and so on. So in general, you could write the momentum space propagator as just I over p squared minus m squared plus I epsilon times the sum from n equals 0 to infinity of, in my notes I had a minus I here, so just put a minus I, so the minus I will cancel with the I. We're left to then segment of p squared over the Feynman propagator to the end. So this is just a geometric series. And we can sum the series. And
for example, the first term is from only that single line, right?
that's right.
And but so we are seeing that as an internal line.
So, okay, good question. So here what we're computing is the greens. So what I'm referring to as G of PP, it's just the Fourier transform of the two-point function of the green. So we can go from G of PP to G of X, Y, which is omega 5x 5y by Fourier transform. And so for the Green's functions, we treat internal lines and external lines in the same way. The reason that we treat them differently when we're calculating matrix elements or scattering amplitudes is because of the LSE reduction formula, which has a Klein-Gordon operator for each of the external particles. And the Klein-Gordon operator will just basically kill one of the Feynman propagators, because the Feynman propagator is a Green's function for the Klein-Gordon operator. So yeah, so yes, when we're calculating Green's functions, we treat all lines the same and write down the propagator for all of them. And so G2 of P is just given by a geometric series, which we can sum. And the result, we just get 1 over 1 minus sigma of P squared. P squared minus M squared plus I epsilon. And this we can simplify. And we get an I over, we just multiply and divide everything, or just multiply this through. We get P squared minus M squared minus sigma of P squared plus I epsilon. And so this is an exact result. We've made no approximations here. Yes?
Why is sigma a function of P squared, not just P, for example?
Okay. Instead of just P. So well, it's going to be Lorentz invariant. So and the only possible thing it can depend on is P. So that's why I've written it as a function of P squared instead of just P. Yes, but if we, yeah, that's the reason. So there's only one possible thing that it can depend on. Okay, so we have this, and this is an exact result. We've made no approximations. And we have an exact formula for the propagator. Of course, that's assuming we knew how to compute sigma, which in general we only know how to do perturbatively. But still, this means if we want to calculate the propagator at some order, instead of calculating all of these diagrams, so for instance, in particular, these bottom, these first three diagrams at the bottom of the board, there's absolutely no reason to ever compute these diagrams, because we know these diagrams are not 1PI diagrams. So if we compute the contribution of all 1PI diagrams at some order, we can encapsulate the effect of these non-1PI diagrams by using this formula. Okay. So we've obtained a very nice exact result, but it doesn't seem to tell us anything directly about what we were interested in, which was seeing what k phi omega being equal to e to the ikx told us about our counter terms, z phi and zm. And to see the relation, I need to quote another result. So this is another exact result that we will derive in QFT. So I'll just state the result. QFT2 will derive this result. So I'll just state the result and the assumptions. And it's not at all obvious how to go from the, it shouldn't, it's not at all obvious to go from the assumptions to the result based on what I'm going to tell you now, but we will come back to this in QFT2 to see where this comes from. And so this exact result is known as the Challian-Lemon spectral representation. And we'll derive in QFT2. But let me just state the result. The result is that G2 of P is I over P squared minus M physical squared plus I epsilon plus an integral from 4 times the physical mass squared over a rho of S, P squared minus S plus I epsilon. And so what is this? So rho of S is what's known as the spectral function. And it contains information about the bound states of the theory. So this integral runs from 4 m phi squared to infinity. If we assume that there are no bound states in the theory. So, and that's one of the assumptions that goes into this derivation. So one is there are no bound states. But this part of the formula really just tells us about the multi-particle states. So this is the most interesting part of this formula for us. And so what this tells us, this first term tells us, is that there is an isolated pole at p squared equals m physical squared. And so m physical squared here is the physical mass of the particle. It's what you would measure in a lab. So m physical is the mass you would measure in a lab. Which, up until now, you probably haven't been worrying about the difference between the mass parameter that shows up in our Lagrangian and the mass you measure in the lab. As, after all, I've made no mention of the distinction between the two up until now. But they're not a priori necessarily the same thing. And they can be different. And So they'll be related, but they're not always the same thing. So here M physical is the physical mass of the theory. And so from this formula, we learned that there's an isolated pole at p squared equals m physical squared. And we also learned that it has residue. With residue I.
One question. This G comes here. Where is it?
The G, the coupling constant,
Yeah.
it will be hidden in the spectral function. Yes, it will definitely be hidden in the spectral function, and depending on your renormalization scheme, it could actually show up here too. Okay, so I've stated one of the assumptions that was necessary to derive this. The other two may be familiar. The other two assumptions are that omega phi, omega is 0, and k phi, omega is e to the ikx. These might be familiar. I hope they are. After all, these are precisely the same assumptions we made to derive the LSE formula. So this result should also hold if our LSE reduction formula assumptions hold. So that means that these two expressions for the momentum space propagator should agree. One of them we computed. The other one I just stated, and we'll again come back to that in QFT2. So what does that tell us about, or how can we use this to determine Z phi and Zm? Okay, so we can make one more choice to make our life simple. So we can set m squared equal to m physical squared. So this is the mass that shows up in our Lagrangian mass parameter. This is the mass we measure. Certainly a consistent thing to do to set them to be the same. So if we want these two things to be the same, then we compare the term we got from the geometric series, the 1pi calculation of the momentum space propagator with our expression over here. We need first of all, we need sigma of m squared to be 0. This is so that G2 has a pole at p squared equals m squared. Call this the 1pi calculation of G2. And so that helps in making the two formula agree. But we also need the residues to agree at p squared equals m squared. So for that to be the case, we also need sigma prime of m squared to be equal to 0. So that the residue of G2 1pi at p squared equals m squared is I. So if these two things are true, then we will have an isolated pole at p squared equals, or at least a pole at p squared equals m squared with residue I. And so if we look over here at how we would calculate sigma. So sigma is just the contribution of the 1pi diagrams without the external legs. So if we wanted to calculate sigma at order g squared, what we need to calculate are just these two diagrams. And this diagram here depends on both z phi and zm. And so I won't show you how that works, but we could use this. These conditions, can use these conditions to fix d phi and zm order by order in G. So those are all the assumptions we made in deriving the LSE formula, and we've used those assumptions to fix 3 of the 4 new parameters we had in our Lagrangian after we shifted and rescaled. But we still have one left. And so ZG should have something to do with the 3-point function. So let's see what we can say about ZG by looking at what's known as the vertex function. And I'll explain what that means in a second. So define the vertex function in momentum space, and we'll just define it to be the sum of all 1pi diagrams of this form, where we have momentum k1, k2, and k3 flowing in. So diagrams of this form are amputated. So there's no corrections to the external legs. They're completely connected. So one particle irreducible diagram is, by definition, connected. So this looks like the same diagrams we would consider if we were computing a matrix element. The difference between the two is that we will not impose, for a vertex function, we do not impose that ki squared is equal to mi squared. We do not impose the mass shell conditions for the particles. So otherwise, it's the same. Same as I am. And why would we do that? So one reason is that if we compute the vertex function, we can use that to compute other or at least some contributions to other matrix elements. So for instance, if we were interested in computing, interested in 2-to-2 scattering, and we knew the vertex function, then computing contributions to the 2-to-2 scattering amplitude of this form would be very easy, because we are not imposing that the external particles are on shell, so internal particles are generally off shell, so we can use vertex functions to compute some of the some of the contributions to scattering amplitudes or higher points, Green's functions. So that's one reason they're interesting. Another reason that they're useful is that often it's technically easier to impose renormalization conditions on the vertex function. And so I'll get to that in a minute. Okay, so how would we compute this in this theory? So at leading order, we just have one diagram. And next to leading order, we have a diagram like this. And so this is a loop diagram. And so there's no way to determine uniquely the momentum on, say, this leg. So I can just give a name to one of these momentum. So this is one of the undetermined momenta that we'll integrate over. Once I've done that, I can determine the rest of the momenta on the internal lines by momentum conservation. So this vertex has momentum L plus K2 flowing in, so it should have L plus K2 flowing out. And over here, this has K1 flowing in and KL flowing out, so it should have L minus K1 also flowing in. And so we can write down the associated expressions for these diagrams. So for the first one, we get IZG times G, plus for the second one, we have IZG G cubed, but we're only working to order G cubed. We should set ZG to 1. And then we have an integral over the undetermined momentum. And propagators for each of the internal lines. So notice that I have not included propagators to the external lines. So I'm defining the vertex function to be in every way the same as the matrix element, except for we're not putting the external particles on shell.
So when you say for vertex functions, do you want those
We do not. I said one thing and wrote the other. Thank you for catching that. We do not. how is this for external particles? So again, I apologize for writing the opposite of what I said. But yes, so the difference is that we do not impose this. But we still only consider 1PI diagrams. So that's another way of phrasing which diagrams contribute to the matrix element. It's only the 1PI diagrams. Those are amputated and completely connected. Okay. So we now have an expression for ZG and G. And what we're missing is a condition that allows us to determine ZG. And there are several options. So one option is we expect, so G tells us the strength of interactions. So we might want to demand that a particular cross-section, or you could demand that, say, some sigma has a particular value. It's related to G in a particular way. That's one way we can impose a condition that would allow us to determine Z. That's more work than we need to do. In practice, it's usually, so to get sigma from V3, we would have to then compute these diagrams at leading order, just be that diagram, and crosses. So we'd also have to compute for example, this one. So that's more work. What we often do in practice is just impose a unphysical renormalization condition. For instance, that V3 of 0, 0, 0 is G. This can be easier. If the particles have mass, there's no physical process in which we have two off-shell particles going to one off-shell particle that we could measure. So this is not something we could directly measure. This will often make the calculations easier, and we'll see a little bit how that works in a tutorial this afternoon.
So, I'm a little lost. What are we doing now with the sigma?
So the LSE reduction formula gave us two conditions, which allowed us to fix three of the Z's, two of the Z's and the Y, three of the four parameters. So if we want to relate our theory to experiment, we should fix them all. So we need one more condition. And we could either impose, so what I'm saying is we could either impose this physical, technically difficult condition, or this unphysical, technically easy condition. If we do either one, then we can regulate our theory, compute any physical quantities we're interested in, and remove a regulator, and then get a finite answer. But we have to impose some renormalization conditions to consistently renormalize our theory.
But on the first condition, like the second one, I cannot see. But the first one, what is that we are asking? We could demand some sigma?
Some particular cross section.
Yes.
So you could define the strength of the interaction by saying that if I scatter two particles with this momentum and they result in two particles with this they result in two particles of this type, then that cross-section has this formula. That's one way we could do it. That would be indirectly related to V and technically difficult. That's what I'm saying.
I think I was going to ask, I think you might have just answered this, but I was going to ask, by that first condition, do you mean we like measure an experiment,
Yes.
its cross-section, and then demand this and use that to find Z?
Yes, so we could, for instance, suppose that, say, a particular cross-section had any formula we like. We say it was G squared times some numbers or whatever.
Okay, and then we like measure that?
We could measure this and then compute this in terms of ZG and G, and then that would give us a condition on ZG.
Do we even need to measure it to do that?
Well, or just demand that the result of an experiment, if somebody did it, would give us this particular result.
But that does involve like experimenting.
Yeah.
Kind of finding it.
And yes. Okay. So this last point is something we'll come back to in tutorial this afternoon and see how it works in some more detail, and in even more detail in QFD2, where we will see one thing we'll see is that this coupling constant, which up until now we've been treating as a constant, actually depends on the energy. So that's one thing we'll see. So let me just summarize and make a few more comments. So what have we seen today? So we've seen that explicitly Y is formally infinite. Z phi and Zm will also turn out to be formally infinite. And depending on the theories, perhaps all of the counterterms could be formally infinite. And so we need to regulate the theory. And there are many ways we could do this. We can introduce a cutoff. We could treat the dimension of space-time as a complex parameter, and we'll see how that works in tutorial this afternoon. We can do some things without worrying about this problem, but in order to, say, compute a cross-section, our cross-sections will, in general, contain diagrams that have these counterterms in them. So if we're interested in cross-section, we can draw a 1pi diagram that contains this counterterm vertex. So we need to understand the counterterms in order to compute scattering amplitudes beyond leading order. And to do that, if they're formally infinite, we need to regulate our theory. And the procedure I've been describing after that is that we should then solve our renormalization conditions. Then we solve renormalization conditions. And what I mean by renormalization conditions, for us, these were the conditions that omega phi omega is 0, k phi omega was 0, which was related to sigma of m squared and sigma prime of m squared being 0. And the last one was just that we impose something about our vertex function. So these are the renormalization conditions. We can solve these for z's and y after we have regulated our theory. And then the claim, which I didn't demonstrate, but is true. Yes, thank you. The claim, which we will see in at least one example in tutorial this afternoon, is that after we do this, if we then step 3 is to compute physical quantities, which will be independent of the regulator. And then we can remove the regulator. So this is step 1, step 2, step 3, and step 4. And we'll go through an example of that in tutorial.
So, didn't we find that y diverges after solving those conditions?
Yes. So
Do you mean that after regulating, they not necessarily like the conditions are not necessarily
well,
satisfied?
after yes. So 1 and 2 we often do together, and 3 and 4 we often do together also. So, but yeah, I can group these together into one step by solving the. Yeah, perhaps you're right that we should do this first. Do that first and do this second. Yeah, and in practice, I think of doing these 2 steps together and then doing these 2 steps together. All right. And so throughout the course, I presented these conditions as sort of the only way to do things. It's true that the LSE reduction formula only has the interpretation that I told you it does if we impose these conditions. We can impose other conditions. The interpretation of many of the formula that I've been discussing throughout this course will change, but sometimes it's technically easier to impose different conditions. So these are, I think, the conceptually clearest, at least these first 2 conditions to impose. So throughout the course, I've been using those. But there are other ways to renormalize. Which will change the interpretation. Ours is called the on-shell. On-shell scheme. And finally, we will come back to all the issues raised in this lecture in QFD2. So there'll be much more of this in QFD2. Any questions on what we've done today? All right. So this is my final lecture. So tomorrow, Tibor will take over and tell you about the quantization of fermions and gauge bosons. What we've done in my half of the course is we've quantized the free scalar field, first few lectures, and then we spent most of my part of the course discussing how to compute observable quantities, scattering amplitudes, and decay rates. So to do that, we learned how to compute. First, we learned how to compute matrix elements, scattering amplitudes and matrix elements, which are related to time-ordered expectation values, which we can compute by going to the interaction picture. So that's where we've gone. And most of these techniques will apply for the cases of fermions and gauge bosons. But there are several new and interesting things that occur when we deal with particles with spin, which Tibor will tell you about. So thank you for your attention.